Hello everyone, welcome back to ECE100 class 13. Last class we talked about Kirchhoff's voltage law and loop analysis. In this class we're going to talk about Kirchhoff's current law and nodal analysis. So let's give you a definition. What is the Kirchhoff's current law or KCL? So let me provide you the definition, then we'll go explain that. So the sum of all currents at a node, you know what a node is zero. What it means, if we add all the node current, let's say, let's do this way, k equal to 1 through n, there should be 0, right? So to make this happen, we need to define, we defined last time voltage drop and voltage rise. Here we have to define what is positive current, what is negative current. So if we take a node, if we say that incoming current is positive, outgoing current is negative. So that means if you take this node over here, so I can see that I have two incoming currents, I3 and 4 amps, and one is outgoing current from the node. So if I add them all together, then it should be 0. So based on this, incoming current is positive, outgoing current is negative, my I3 should be positive, and my 4 amp should be also positive, then my 4.75 amp should be negative. So then if I add them all together, I get 0. So that means that your I3 would be 0.75 amps. So that's how you apply KCL at a node. In general, if you might not have a low node, but if you have a closed boundary, like this one here, this is a closed boundary right here. So we can apply the same definition for the closed boundary also. So how to do that? Sum of all branch current across a closed boundary is 0. So now that means that, let's say for this one here, if this current is I1 going into the closed boundary there and coming, this one is I2, then your I1 is positive, is going in, I2 is negative, is coming out, it should be equal to 0, all right? And we're going to do this in the class, so we're going to wait until the class, and also going to do this in the class. So now, after that KCL, we're going to apply that KCL for nodal analysis. All right. So what is that? To use a nodal analysis, you have to first find all the nodes in the circuit. And once you find all the nodes at the circuit, then you have to assign the levels like VA, VB, or V1, V2, V3 for all the nodes. Those are the voltages at the node. Then you have to define one of the node as reference node. We use the reference node to measure all other node voltage. Normally we assign 0 voltage for the reference node. Then you'll use the KCL for each of the node. Then we'll solve the equations to find all the currents, voltage, and all other parameters of the circuit. So to do that, let's use this one here. Let's see how many nodes are here. Some nodes might not be useful to solve the problem, but we can go through this. Let's see how many nodes we have here first. So let's say that I can see that there's a node over here, right? And there's a node over here. There is a node over here, and there's also a node over here. So you can see that we can use all the nodes if we want, but this node over here the current going through 18 ohms and 6 ohms, they're the same current, so I don't have to use these nodes for my solution because the both branches are carrying the same current. So let's say this is my VA, this is my VV, and I'm going to use this negative side of this power supply as a reference node, so it's V reference. V reference is always we assign 0 voltage for the circuit solution. So now, once you know all the nodes, then also you need to find, look around, see is there any node voltage is known. So reference is known because we assign 0 volts for the reference. Then if this is 0, there's a 6 volts difference across the source here. If this side is 0, this side should be 6 volts, right? So then I can say that VA is your 6 volts, right? So I know that. If you know the voltage for a node, you don't have to apply KCL to solve anything, but our goal is to find the node voltage. So if I know it, I don't have to do anything with the node. So now, after I've done that, now let's assign the current for each of the branch. So let's say this is my I1. Let's say this is my I2. I'm also assigning the direction, you can see that. This is my I3. As I said, 18 ohms and 6 ohms both have the same current I3, so I don't have to do anything with this node for the circuit solution. So out of 4 nodes I have, 2 nodes has the known voltage, like reference volts has 0 volts and VA has 6 volts. I don't have to do anything with these nodes because I know the voltage. Another one is not necessary for the circuit, so I have only 1 node that I have to deal with. That is node B. So I'm going to apply KCL at node B. So as you know that for KCL, if we add all the current, that should be 0. And we also said that incoming current is positive, outgoing current is negative. So for this over here, so I1 is incoming current, it's positive. And I2 is negative because outgoing. I3 also negative because outgoing, right? Okay. So now, for the current, I1 is between node A and node B. So current is the I1 going through 18 ohms, so I need to know the voltage across 18 ohm, divide by resistance will give you the current I1. So I1 is the voltage difference across that 18 ohms and divide by the 18 ohms resistance. So I1 is VA minus VV over 18. Can you see that? So 18 is a resistance, then voltage difference between A and B is across the 18 ohms. So voltage across the 18 ohms divided by resistance will give you the current. That's Ohm's law. And for I2 is between node B and the reference. So is the reference is 0 volts. So that would be VV minus 0 volts over 12. That's your I2. For I3, that is, I can add 18 ohms and 6 ohms in series because they're in series. So that would be 24 ohms here. Then I have VV minus 0. So that's how you do the node equation now. So as you know that I know VA, which is 6 minus VV over 18, VV over 12, VV over 24, that equal to 0. So now I have only one equations and one unknown, so I can easily solve it to find the VB. If I go through the solutions, we're gonna test it. If I go through the solution over here, I should get VB is 1.85 volts. All right. Then once you know that, now you can find all the currents you want. You can find, we're looking for current through, let's go back. We're looking for the current through 12 ohm resistor here, which is this one here. So that is basically I2, which is VV minus 0 over 12. So I can easily find it over here. So I2 is VV over 12. I know VV, which is 1.85 over 12. That will give you 0.154 amps. So that is the current through 12 ohms. You can also find the current through 18 ohms. So current (18 ohms) would be, that's your I1. That is VV VA minus VB over 18. So your VA is 6 minus 1.85 over 18. So your I1 would be, let's find it out here. I1 would be 6 minus 1.85 divided by 18 will give you 0.2306 amps. That's your I1 current through 18. You can find all other current as long as you know how to do it. All right. And we'll solve this problem in the class. And also, we're going to solve this problem in the class also. So all other problem here, those are all. We're going to talk about the supernodes a little bit here. What are the supernodes? So if you have a voltage between two nodes, voltage source between two nodes is called supernode. How to deal with this? So over here, if you look at that here, let's say this is your VA, and this is your VB, and let's say this is your VC, and this is your reference, which is 0 volts, right? So how do you deal with the supernodes here? So there's a voltage source between node B and C. So I know that your VA is 7 volts, as we discussed in the last slides, 7 volts. Then VV minus VC, it would be your voltage difference right there, so it would be negative 2 volts, or you can do it VC minus VV, which would be 2, right? So that is the relations between these two nodes here. So the supernodes, we're gonna take this as a one nodes here for the calculations, and we're gonna go from there. So if I do that, so if I take this whole thing as a one node, right, and I know that VA here, VV here, VC here, right, and this is my reference node, which is my 0 volts. So now let the current here I1. Let's say this current is here I2, and let's say this current here is I3. So if I use the KCL at supernode, so KCL at supernode, if I do that, then I see I1 is coming in, so I1 minus I2 minus I3 should be equal to 0. Let me take this, let me do it nicely here. So the supernode is right here. So now you can see all the current going in and coming out of the supernode. So now I1 right here is it would be VA minus VB over 18, right? Then I2 is right here is VB minus 0 over 12, and over here you have now I3 is VC over 6 equal to 0. So I know the VA is my 7 volts, and VC minus VV is my 2 volts, right? So, and also I can do it over here. I can take one off. I can say this VC is what? 2 plus VV, right? So if I take this and put it back here, so it's a 7 minus VV over 18, VV over 12. Over here, your VC is 2 plus VV over 6 equal to 0. Now look at that. It has a single unknown over there. That is your VV. So if I solve it, I should get the value for VV, which is your 0.182 volts. Once you know VV, you can easily find VC, which is 2 plus VV, which is 2.182 volts, and so on. So now if you know, now you know all the voltages, you know VC, you know VV, you know VA, then you can easily find I1, I2, I3, all the current you're looking for. So that's a supernode. If you have a voltage source between two nodes, you can use that as a supernode and go from there. All right, all those things we're gonna solve in the class. So that's all for this KCL lecture, and I'm gonna see you in like